Good morning, everyone, or good afternoon, depending where you are connected from. Thank you for joining today. This is the third webinar series from the IGCP SIG36 project. It's a project funded by UNESCO through the International Geoscience Program. All the webinars are recorded, and after the webinar, I will upload the recording on the YouTube channel. I will send the link in the chat later during the presentation. If you have any question for the speakers today, you can write in the chat, and at the end of their talks, we can ask them the questions. So if you have any comments, anything is welcome. So today we are with Professor Antonio Galgaro and the PhD candidate Mohammadan Azimi from Padova. And they are from the research group of the Universidad de Padova in Italy, and they are going to talk us about a closed-loop solution for geothermal power production. It's a really interesting topic in the geothermal industry. It's an emerging topic, I would say. So I think it's a really interesting topic for today. So thank you very much for joining, for your time. And we can start with Professor Antonio.
Okay. Thank you very much for your presence and your interest. And hello to everybody. I start with a short introduction regarding the closed-loop geothermal solution that permits to avoid the direct extraction of fluids from the ground that require a lot of problems of management of these hot fluids, rich of gases, not condensable gases, and other minerals that are not so friendly in terms of sustainability, environmental sustainability. So, in particular, there are a lot of just existing structures, such as old oil and gas wells, sterile or abandoned after uses, that can be reused and adapted for geothermal solutions. I only show you some situation, particularly in Italy, where we have a lot of these wells not anymore used or never used in the past, only drilled and minerally closed, but it's possible to reactivate it for geothermal uses. In particular, sorry, okay. In particular, this solution can help to reduce the CO2 emissions thanks to the possibility to produce not only heat for instance, district heating when is the needs of heating in particular are very connected with the climate conditions, but even for electric power production. So the double uses is possible, obviously, if the geothermal conditions permit. In particular, we have evaluated in Europe, in the extended Europe, 27 countries. That's one of the most important requirement in terms of energy is the heating of households, residential heating, and even electricity in residential, but not only type of users. The oil and gas production is often linked with a large volume of waters, and a lot of cases due to the depth of these wells, the temperature are higher than 100 degrees. And the residual fluids after hydrocarbon uses is water. So there is a sort of resource of heat and the fluids that permits to transfer the heat from the depth, from the bottom of these wells until the surface. In this case, I have no emission of CO2 if I use reuse of these wells and closed loop solutions that permits to, thanks to the circulation of fluids into the wells, abstract heat from the ground and use the heat for the all the uses of the stakeholders, particular electric power or direct use of heat. Even the industries can use this solution for heat needs for the production processes, or for heating of houses, or for instance in agriculture fields such as greenhouses or fish farms. Taking account the temperature of the wells change obviously the use, but during our research we evaluated the higher temperature conditions. The information is available thanks to the hydrocarbons drilling database, and is possible to adapt these wells in different ways to abstract heat. In these slides, you can see the different type of solutions. I evaluate or show you the general aspect of the double pipe heat exchangers or U-tube, and the coaxial solution will be explained, shown by and described by Dan Azimi, that is the PhD student in the last year of his adventure, scientific adventure, and he will show you the results of obtained by his studies, in particular in high temperature environments. So I will see you only the middle of the three type of solution. Maybe I can use two wells that are close one to the other. One for abstraction, one for reinjection. Is an open loop system, but the closed loop are divided in two main big families. The one is the U-tubes, a sort of couple of wells that are connected after the refurbished of the two vertical parts horizontally to permit to obtain the higher efficiency of the heat exchanger process, or the coaxial systems that permit to use the only one borehole to abstract heat. To transform the heat in electric power, we need as high as possible temperature of the fluids, and I can use a sort of binary cycle called ORC, organic ranking cycle, that permits to transform heat in electric power. And Dan will show you this type of solution. There are different type of coupling of the two boreholes. I can use the simple tube to connect the two boreholes, vertical boreholes, or create a sort of radiators. This technique is developed by a Canadian company, Ever, that is applying in Germany one of the first example in the world, and they are quite finishing the first phase of this radiator. The techniques of directional boreholes is derived by oil and gas practice. So maybe a lot of drilling techniques derived from oil and gas, hydrocarbons research, and wells techniques, and adapt for geothermal uses. In Italy, we have particular zones that are interested for the hydrocarbon research, and you can see the sort of lines on the middle of the plain in the northern part of Italy, and all the eastern part of our country. But in this case, I have a lot of boreholes realized onshore and offshore in this site, but the higher temperature zone is in the other side, in the western part, where I have Larderello, that is one of the most known geothermal area in the world. The first electric power production from geothermal source was performed here in 1904, and in the other countries, other regions in the southern part, I have the Vesuvian areas where I have volcanic areas, and the Etna volcano and the Aeolian Islands, and all the hot spots in Italy are in the western part. So I have sort of difference between the hydrocarbons prone areas in the eastern part and the hottest grounds in the western. This happened because obviously the higher temperature into the ground is not adapted to host hydrocarbons, because hydrocarbons molecular has been destroyed by high temperature. But in any case, I have in a lot of cases temperature more than 100 degrees that can be used for geothermal purposes. This is a sort of very summarized distribution of the 8,000 boreholes from 2,000 meter depth until 6,000 meter, realized in the 17 and 18 years for hydrocarbon purposes. Most of them are abandoned due to the sterility after drilling, or after depletion of the hydrocarbons. Part of them show interesting temperature and are close to the urban areas where it's possible to use not only for electric power production, but for heating distribution. In particular, some of them are realized in the western part, where I have higher temperature, higher geothermal gradients that correspond to this part of this oil and gas, ex-oil and gas wells, with geothermal gradient more than 5 degrees for kilometers, and 50 degrees for kilometers until 70. In this case, I have very high temperature, and it could be very interesting. But even in the Po Plain region, is a northern part of Italy, there are interesting cases close to Milan, where there are boreholes with very high temperature at more than 100 degrees. Around this is the distribution of the boreholes temperature, and in the Milan I have this type of availability of temperature from 150 and 180. That can be used for electric power production and heat distribution in the heating network. In particular, one area is very interesting because it is not only close to the district heating systems, but even closer to the vast industrial heat sources, such as glass farm, that permits to a sort of recharge of temperature of heat into the ground, thanks to the presence of different boreholes, and maybe by switching between them, use for storage during one season and production during the others. This is the example of the U shape. The higher temperature level is crossed by the horizontal part of the trench of connection between two just existing boreholes, and this permits to a very reduced increasing of cost to along the path in the higher temperature zones. because the main process that permits the heat transfer is the conduction, and the conduction has some problem due to the cooling effect in the surrounding of the boreholes that affect in the time the outlet temperature. Dan will explain better than me this aspect. This is one of the most important constraints of the closed loop solution. So we try to detect how we can overcome this limit of the conduction, and there are some options that permit to during the adaptation of the just existing boreholes to increase the efficiency of the system, maybe by insulation of the part of the boreholes, where maybe the shallower part, where I have the most heat losses, or along the just existing borehole to intercept a higher temperature and depth, or change the flow rates, the flow rate of the heat carrier fluid inside the boreholes, and this permits to balance the cooling effect and the energy abstraction. These are a particular case in northern part of Milan, and there are different type of sensitivity analysis changing different parameters to evaluate how is the best way to obtain the maximum efficiency in terms of energy abstraction and maximum temperature, because if I overcome 80-90 degrees, I'm able to produce electric power and not only distribute the heat for direct uses. But now I finished my part with a sort of comparison of cost of the retrofit of an existing well or drilling a new well. In this case, an example of 2,000 meter depth boreholes with the application of Monte Carlo simulation show that the medium cost of a well of 2,000 meter depth is around 8 million euros. You can convert in your current money, or if I choose the retrofit of an existing well, the costs are less than half of 4 million euros. This permits to evaluate the feasibility of this situation, of these particular conditions, to reuse the oil and gas wells, because the cost of the adaptation are quite half of the realization of new boreholes. There are different type of information that we will share with you, because the presentation will be not only visible in the video recorded, but we can share with you even the presentation if you need some information regarding this aspect. So thanks to the attention, and I ask to Dan to continue the conference, the webinar. Thank you.
Okay, thank you very much. Hi everyone, and thank you for being here for this webinar section. And I'll try to share my screen. Just a second. Okay. Okay, I hope everyone is seeing my screen, and in case
Yes.
there is any technical
Everything is
problem,
fine.
please. Okay. So as Professor Gargaro clearly elaborated and made the general introduction, I will try to talk about the implementation of geothermal energy in high enthalpy environment. So as we can see here in this graph, it's the world map of island, isolated island, showing the use of renewable energy solutions. And like sorts of example, I try to point out areas or island where they implemented, they successfully implemented geothermal energy. One of the case study is Iceland, and Huawei, and also New Zealand. Well, going into the focus of this presentation, I'll be talking about closed loop coaxial borehole heat exchangers. Let me take this one. And as you can see from the geometry, it is made up of a single well closed at the bottom, in which a heat carrier fluid can be injected to the annulus space, and on its way down, it can exchange heat mainly by conduction with the surrounding ground, and then comes out to the center of the production pipe. In the following slide, I will try to present some case studies I implemented and also compare some existing study where they also conducted a similar, let's say, numerical simulation of coaxial borehole, but in that case, they limit themselves in just a constant temperature or constant thermophysical property of the heat carrier fluid. So here is outlined the different case studies. One will be the Kafla in Iceland, where we will see the effect of the thermophysical properties of the heat carrier fluid. In this case, will be water. And then the second case study will be the Ferrara case study, where I'll try to point out the effect of the flow rate and also the insulation of the turbine, that is the production pipe at the center. And finally, my case study of my PhD. Okay, let's proceed. For the first case study in Iceland, as I observe in this figure, is one of the more advanced, let's say, region in the implementation of geothermal energy. And here is a representation of the conventional usage of geothermal energy. And here the geothermal fluid deep in the ground and close even to magma, where they extract this water directly into a turbine, produce electricity, and then we inject it. But I think a few years ago they encountered some technical problem, and the geothermal plant in Kafla had this problem where there was a sort of high pressure condition, and it blew out the casing of the well. And nowadays they are trying to investigate solutions in order to let's say to remedy this technical solution. And one of the solution, as I mentioned earlier, is the use of coaxial closed loop with borehole heat exchanger. And from the work already done by Renaud et al., they implemented this solution, and the results obtained with the numerical code, numerical final element code, and the software. They observed that that is the solution can be implemented, but in this case they use a constant water properties. So to try to investigate the effect of these properties, that is the thermophysical properties of water, we implemented the same case in the final element software COMSOL multiphysics, in which we integrated the variation of the thermophysical property of water with temperature and pressure, and we observed that the result is quite improved. It's improved compared to their own results. So in this case, it will be important for the feasibility and cost-effective analysis to take into account this parameter, that is the thermophysical property variation of the heat carrier fluid with temperature. In the second case, the case of Ferrara, for just a little introduction, the Ferrara case, which is working nowadays, they use the conventional extraction and injection geothermal system, and they also implemented a sort of hybrid network in which, in addition to geothermal, they use also biogas and also solar panels to increase the efficiency, that is the provision of the heating water to the city. In this case, they are now also trying to implement a coaxial solution, because due to the extraction of water injection, they observe that there is a sort of reduce, that is the reservoir is being depleted. So they are finding solution in order to maintain a constant and a long-term provision of geothermal energy to the system. In this case, we try to investigate the application of coaxial closed-loop solution. The bottom hole temperature is around 180 degrees Celsius. And here is the geometric parameters and the operational parameters used in this. We try to simulate this solution in the case of Ferrara geothermal solutions. And here is a representation of the fluid, the evolution of the fluid temperature inside the heat carrier fluid, which is water inside the pipe, the coaxial pipe, with respect to different injection flow rate. As we can observe, the injection temperature we implemented is 90 degrees. And you see that since the injection temperature is having higher temperature compared to the surrounding at the shallower depth, it is losing heat to the surrounding till a depth at which there is equilibrium of temperature between the surrounding soil and the fluid inside the pipe. It is being heated up and then comes out to the central pipe. And we can observe that there's also heat loss. That is, there's heat loss between the fluid inside the central pipe because it is hotter compared to the fluid at the annular space. Now, we try to investigate the effect of insulating the central pipe by applying a VIT, that is vacuum insulating turbine solution. And we observe that the outlet temperature is quite improved, is highly improved. That is, the heat loss is reduced. Here in the following slide, sorry. In the next slide, it's the representation of the evolution of the outlet temperature with respect to time for the different injection temperatures. So we observe that for lower, if we want to have a high temperature at the outlet, we need to inject also a high injection temperature. But this needs a sort of cost-effective analysis in order to determine the optimal injection temperature and flow rate for the efficiency of the system. Similar result, we can observe that when there is no improved inner pipe insulation, you see that the temperature at the outlet is quite less compared to when there is a perfect insulation of the inner pipe, due to the reduce of heat losses between the heat inside the turbine and that of the annulus. Similar result is obtained with the extracted thermal power, that is similar trend, because the extracted power is a product of the flow rate, the heat capacity, and the difference between the inlet and the outlet temperature. Now, getting inside my case study of my PhD course, I am implementing this coaxial solution in Ireland. So, as we can observe, most of the islands worldwide are isolated from Jambeland, and these areas are highly dependent on Jambeland for their energy needs and also potable water needs. So investigation by the National Institute of Geophysics and Volcanology, we observed that from one of these wells, we can have high temperature at just shallow depth. So this is quite a high enthalpy anomaly, and it is highly favorable for geothermal implementation. In this regard, we are proposing this solution in order to make the island independent from electricity and potable water needs. So we will implement the coastal solution where the heat extracted, if not high enough, that is, the outlet temperature is not greater than 100 degrees, that can be directly expanded into a turbine. We can use a secondary heat exchanger system and ORC plant, where there's a secondary fluid that can evaporate at lower temperature, and this secondary fluid can be expanded inside a turbine to generate electricity. And now the residual fluid, temperature fluid, can be directed to a desalination plant to desalinate water from the sea and produce potable water for the island. So here is the parameters we set and introduce inside our final element model software, and the positional parameters for this presentation is an inlet temperature of 90 degrees, because the aim is to produce electricity. So we try to impose a high injection temperature and observe what will be the resulting outlet temperature, and lower flow rate also. And the simulation was done for 25 years, approximately 10,000 days. The bottom hole temperature, because since from the previous graph I showed, we have a lower temperature at about 200 meter depth, due to the fact that new site characterization are going on, so we don't have the extension of this temperature profile at deeper depth. So we try to implement a sort of constant geothermal gradient for 400 meter depth borehole heat exchanger. 400, why? Because from the regulation, and also due to the fact that Volcano Island and also all the island worldwide, I guess, is UNESCO protected. So the minimum borehole depth, let's say the authorization or regulation could be easy, is a 400 meters. So we first start with this, and then later we also try to show, in that case, to show that going deeper we can have more, we can extract more heat, because going deep we have more high temperature. So setting this simulation, this geometry inside the borehole, inside the final element software, here is the result, as I explained earlier, the result obtained for a borehole depth of 400 meter depth, 600 meter depth, 800 and 1000 meter depth. As we can observe in this graph, with 400 meter depth, the extracted electric power is quite low if you want to really provide electricity for the island, though it is just one borehole. But as we go those 200 meter further, that is editable to increase the borehole depth, we observe that we get about 3.2 megawatt electric power. Getting more deeper, for sure, we encounter higher temperature, and also the volume of fluid that is in contact with surrounding is also increased. That is also the resident time of the fluid inside the ground is also increased. So it had more time to extract heat with the surrounding. So this is the effect of the borehole depth. Coupling to the fact that in the previous case studies where I showed the effect of flow rate and injection temperature. So having this enable to try to have a sort of sensitivity analysis to understand which combination of all these parameters enable to obtain the best and cost-effective energy solution for the island. Maybe I have been fast, and more development can be done in the question and answer section. Pardon. Here is the Geothermal research group of the University of Padua, and here is the end of the presentation. Please feel free to ask any question. It will be a pleasure for me and also Professor to try to answer it. Thank you for your attention.
Thank you very much, Antonio and Danasimi. If the people that are here listening to the webinar have some questions, can write them in the chat. In the meanwhile, I will ask you yes, a couple of questions before for Antonio about the Trecate case study. I didn't know about it. Is it active right now? Does it generate heat or electricity for the nearby city, or what is the current situation of this case of this site in Trecate?
Now is one of the most interesting for ENI, our national oil and gas company, for the experimental pilot site. The company is involved in a new proposal European project regarding just this item. So they participated to this European call with us and other partners in Europe. But now is only a feasibility analysis available. But I think that in maybe 2-3 years, the plant will be realized as pilot plant. Okay, I see. Okay, thank you, Antonio. And for Dan, I wrote down 2 questions. The first one is when you show the comparison between the ANSYS and COMSOL results. I think it was for Island study or Ferrara, I don't remember.
This one, yes.
Okay, what I didn't understand very well. What are the main difference between the 2 software based on your experience simulating this kind of scenario?
Okay, for the Iceland case, in the numerical simulation, as you can see, the properties is a constant, like the water property are constant. So implementing it does not, because as the heat, the water is injected in the alumnus, it goes down, it is exchanging heat with the surrounding, temperature also changes. So the water properties is not constant. That is the assumption from their own simulation, they assume that the water property is constant. In our case, we implemented a time-dependent property of the water inside. I see. Yes, as you can see here, just the scaling they use is to compress the scale, the horizontal scale, but it's the same. We implemented the same boundary conditions, just the physical property of water that is dependent on the temperature that we implemented, and we simulated and we observed that all the temperature is quite improved because temperature change, density of water changes with temperature, even the capacity change with temperature, the thermal conductivity also changes temperature. And these properties have been an inbuilt material properties already existing in COMSOL. So we just implemented and we observed that the result is quite improved.
Okay, and what about the insulation material that you use in COMSOL? What kind of material and thickness you use for the insulation that you use to compare the well alone and with, I think, yes, in the next slides.
This one?
Yeah, the insulation is, okay.
Yeah, the insulation material we use is the first result, that is this one. Yeah. Is used with this initial material property. And now improved insulation is used with VIT, vacuum insulating turbine, that is made of 2 sheets of steel, and in between this sheet is air, like this. It is just air, because air is poor conducting material. So it is just air that is between two sheets. It's air that is existing. So when we observe that this insulation quite improve the outlet temperature. That is, it reduces the thermal short circuiting between the 2 feet downward and upward.
Okay, so we have some questions in the chat. Maybe you can also read them. The first one is from Jasmine about the feasibility of electricity production using deep closed loops. Heat exchanger looks okay, but economics is more questionable. These systems are very expensive and power production may not be economically viable. Do you have results to share on the economics of those systems? Is the first question. Maybe, yes, both of you can answer or give your opinion.
For me or Dan, Daniela? If I can start the answer, we provide a sort of first raw evaluation because there are very few examples, quite nothing, but there are other aspects to take in account, not only the practical cost, but the reduction of mineral risk due to the fact that I just know the geological situation thanks to the data obtained by just existing wells. And this permits to facilitate the financial aspects because if I reduce the mineral risk, I'm just prone to financial covering because the risk is lower than the other situation when I drill without nothing without having direct informations on the site. But I just show you that the first evaluation obtained by Ferrara, because in Ferrara is a town in the northern center part of Italy. There is a district heating based on a geothermal system with starting from all the oil and gas well used as for the injection now, and other 2 wells that are used for abstraction. The temperature is around 100 degrees, and we have obtained these values of half cost of adaptation of existing well with the same characteristics if compared with the new drilling costs. This is just a good results because there are not other informations available in the references, and this could be a good start to evaluate in depth. The European project that we are preparing just regard these aspects, the regulatory, because there are not rules regarding the reuse of wells in the Europe, and there are no informations about the real cost of adaptation that change in front of the different type of wells. So we need to cover this lack of information, and the new project aims to that.
Thank you, Antonio. There are 2 more questions from Hamza. What are the expected electrical capacity that you are targeting with this kind of system? How many megawatts?
Maybe let me try to give the first answer. For sure, maybe Professor Gagao will develop more. In the case of Volcano Island, the minimum is 1 megawatt electricity for 1 borehole. But as we said, the depth constraint, as you say from the start, the authorization there is 400 meters. So with this 400, you just have about 0.8 megawatt electricity, and also the flow rate is quite low. And when you increase the flow rate, the outlet power, the outlet temperature also decreases, and consequently the extracted electric power also decreases. So in that case, we are trying to investigate like other solutions, maybe try to implement a sort of array, borehole array, maybe 4 or 6, depending on the final heat electric power demand, because it's still to be characterized. Having this borehole array will permit us to like have an intermittent operation for each borehole, or coupling maybe 3 to attain the required temperature outlet power. And due to the fact that why extracting heat, the surrounding ground also cools down, and why with time the power extracted also decreases. So having also this solution permits us to maintain a constant production by shutting down maybe these 3 and then operating the other 3. This permits the first in the first case the recharge, that is the ground recovers not its total initial temperature, but at least maybe 90% of the temperature, so that after the maybe 6 months of operation of the other set of boreholes, you make a sort of intermittent operation. But it is quite it's still a feasibility study. So for the first case, for one borehole, we are targeting at least 1 megawatt electric power.
Sorry, Daniel, I answer to Jasmine and Professor Hamza. Yes, the poor conduction that is on the base, the main heat transfer process of the closed loop system is not so efficient like use directly the hydrothermal fluids. But thanks to the new drilling techniques that permit to reduce the cost at high depth, it's possible to intercept higher temperature that permit to obtain enough temperature useful for electric power production in efficient way and economical feasibility. So obviously there are some constraints to overcome, and we are changing the type of heat exchangers, increasing the depth, or realizing the directional drilling derived by oil and gas techniques to along the productive and deeper part of the boreholes. But I think that could be a good option to overcome the problem related to the management of the geothermal fluids and social acceptance, because the social acceptance is strictly related to the collateral effects due to the use of open loop systems, such as induced seismicity or subsidence, or pollution of the shallower drinking of water uses for irrigations, and so on. This is maybe the future, and obviously there are some constraints that I think that in a short time means some years, will be overcome. And thanks to your observation, it's true. It's true. The problems are really existing.
Thank you. I think there is the last question from Kader is partially related to what I asked you before about the pilot site for direct application using wells, using old oil and gas well. I think so. There is this Trecate pilot site, right? But it's not operating right now. It should be maybe in a couple of years, as you mentioned. there are other sites in Italy that are studied?
Actually not, because quite all the wells are of ENI, and in the past they are not interested to use these structures, but now, thanks to the transition to renewable energies, the interest is increasing. So thanks to this interest, we are exploring the feasibility, and one of the first example in Italy, sure, that are not existing now, is Trecate, and maybe in the Latium region, northern part, there are other cases. These are the most prone with a higher temperature and the most useful conditions to adapt. But there are some drilling companies that are very interested to develop techniques economically feasible to adapt oil and gas wells to as geothermal. One of them will participate to the proposal, European proposal of the call. And there are other drilling companies, oil and gas drilling companies, that like to open to this possibility.
Okay, thank you. This is like a positive message for the future. We hope that maybe there will be the reality, answering also the title of the webinar, if it's might or reality. So I think we all hope that this transition from oil and gas and geothermal can be a reality soon in some years, so not a short, medium term. Okay, I think we answered all the questions. Thank you very much, Antonio and Dan, for your time, for sharing your research, and to all the people that joined here today. Hamza also writes you, Antonio, for a possible future collaboration. Hamza is a researcher from Algeria. It's part of the IGCP network. So yes, I can send you, Hamza, the contact, Antonio's contact, and you can keep in touch. I don't know if you want to add something, Dan or Antonio, and we can close the session.
We only wish to thanks to all the participants, because it's a new item, maybe with some problems, but we are confident that the future will be even in this way. And thanks for the questions that are very interesting, because they are competent to the effective item. Thank you very much.
Yeah, thank you very much. And we remain open for any collaboration. Thank you.
Okay, thank you very much. Bye. Have a nice day, evening.
Thank
Bye.
you.
Bye.
Bye-bye.